So now let's look at resist, contrast, and sensitivity. So for the resist, so I'm sure you have learned this for the way you learned photolithography last term. For the resist, so we coat the resist film on top of substrate. Then we do the exposure, then we do the development. So, and you know, for the casing of the positive resist, for this one positive resist, also A and B, they are positive resist. So after exposure and development, so this part will be developed, and this you have this is the remaining thickness. So the axis here, so this one is the remaining thickness. So normally we also use the normalized remaining thickness. So it's the same thing. So as you know, for the casing of positive resist, so we have higher dose, this one will be developed to the bottom. So this thickness will become 0. So you have here. We have low dose, the thickness is a full thickness. This is like 100% thickness. So this is the case for the positive resist. For the negative resist, so higher dose will make all the resist remaining, and low dose make all the resist is gone after development. So now let's define a sensitivity. So for the casing of the positive resist, the sensitivity is defined as a D1 value. So it is the dose for the fully development. You can see it here or you can see it here. It doesn't matter. This one people also call it as the clearance dose, but it's the same thing. Sensitivity or clearance dose is the same thing. It can be even here or here. It is okay. For the negative resist, so one way to define the sensitivity is that, so we take the 50%, if this is 0.5. So this is 0.5. So 50% remaining thickness. So this dose here. So this dose here is defined as the sensitivity for the negative resist. So this is the 50% remaining thickness. So the contrast define how the transition from the undeveloped to the developed. The transition here, this is the definition for the contrast. So obviously, ideally, we want a very sharp transition. For example, something like this. Ideally, we want this sharp transition. But in reality, we have the slope. So this transition slope define the contrast. So you draw a line here for the casing of B. So for the casing of B, you draw a line here. This way you have a D1 value. And this one, the turning point here is the D0 value. The contrast is defined as 1 over log 10 D1 over D0. So as you can see here, for the ideal case, for this one, this is ideal case. Ideal case, D1 and D0 is the same. So then this one and this one, they are same. So you have log 10, 1. So this is the 0. You get the infinity. For the perfect resist, the sensitivity is infinity. So normally we want gamma to be higher than 2, and for the casing of PMA high resolution resist, we want the contrast is normally 5 to 10. So now let's look at, so we have the positive resist and the negative resist. Now we want to see which resist we should choose. So this depends on what pattern you want to make. For example, if you want to make isolated sparse patterns, the positive resist will be good for the lift-off. If you want to make the metal structure like this or silicon structure like this, you coat the resist, you do the lithography, you coat the metal, you dissolve the green color resist, you have the metal. Or you can do the pattern transfer down to the substrate. So that's good for the positive resist. For the casing of the direct edge, if you want to do the direct edge, we need to use the negative resist because you have the sparse pattern. So you only need to expose this area. You expose this area, then you use the resist as the mask to etch into the substrate. So sometimes, very often we have only one resist. We have only one positive resist. That is PMA. How to make the opposite patterns? This can be done by a process I call it as the double lift-off. So in this case, so we use double layer over the polymer. The top layer is the resist. The bottom layer is I call it the under layer. This can be a polymer such as the PMDI, polydimethyl glutamate. So you do the lithography, then you do the lift-off over hard mask material like chrome or oxide. Then you use this hard mask material as the mask, etch into the bottom polymer layer. Then you can coat the metal and do the lift-off. then you have the metal coated here. So this way, you get the whole pattern in the lift-off. If you can see here, if you do only one lift-off, you get the dot or pillar pattern in the metal. But when you do the double lift-off process, you get the whole patterns in the metal. So now let's look at the sensitivity. Sensitivity again. So obviously the sensitivity is the property of the resist, but it is not only the property of the resist. So other parameters, other experimental parameters will also affect the sensitivity. The first one is the electron energy. So this one we have seen it before. So higher energy, you need more doses. So this is because, as we said, so this is the resist, and this is the silicon substrate. So we have higher energy electron just pass through very, very fast. So the interaction with the resist will be less. So you need a higher dose for the exposure. For instance, for the case of PMA at 30 keV, we need 250 microcoulomb per square centimeter. At 100 keV, you need 600 microcoulomb per square centimeter. So this is what we have seen it before. So the sensitivity also depends on the substrate material. So as you can imagine, if the substrate here, I said the substrate is silicon. So if the substrate is gold, so we know that gold is very heavy metal with high atomic number. So there will be a lot of backscattering. The backscattering will be a lot because gold is like a very high atomic number. So when electron come in, there will be a lot of backscattered electrons. But those backscattered electrons will also contribute to the exposure of the resist. As a result, we need less primary electron beam to expose the pattern because we have a lot of exposure done by the backscattered electrons. As a result, the sensitivity is higher by a factor of roughly 2 compared to the silicon. So here, you should remember that when we talk about high sensitivity, that means we need lower dose. That is high sensitivity. So in addition, the sensitivity also depends on the process conditions. For example, for the case of the chemically amplified resist, so this depends on the post-exposure baking. Because for the chemically amplified resist, the post-exposure baking will induce most of the chemical reaction. The strength of the developer, obviously, for the case of the positive resist, the stronger the developer is, the less dose you will need. The development temperature, the higher temperature, the less dose you will need for the case of the positive resist. If you are using the negative resist, it will be the opposite. For the negative resist, as you can imagine, if the development temperature is higher, the developer will become stronger. Then you will need a higher dose to do the exposure. This way you get lower sensitivity. So for negative resist, higher temperature, lower sensitivity. For the case of the positive resist, it is the opposite. And also development time. We have if the time is infinitely long, the sensitivity will become extremely high. So to show how this works, you can see this one. For example, now we look at this contrast curve B. So this one is developed with 1 minute development time. 1 minute development time. This one is 1.0. That means fully remaining. This one 0.9. That means 90% of the resist remained. So as you can imagine, if we do a 10 minute, if we do 10 minutes, so here is 1 minute development. If we do 10 minute development, what will be the contrast curve? So you can see, you look at, for example, you look at this spot, you look at here. So 10 minutes, you look at here. So for this one, for 1 minute development, we have 0.9 left. That means so 1 minute will remove 10% of the resist. So 1 minute remove 10% of the resist. We have 10 minutes development of all the resist will be gone. So that means it will come to here. So the contrast curve will become like this. So we'll do the 10 minute development. If we do 100 minutes, it may become here. So as you can see, so the longer the development time, the smaller dose you will need. So this is what I said here. So if you have infinitely long time, then the sensitivity will become infinite, zero. We need a zero dose. And lastly, so obviously, the sensitivity also depends on the developer used. For example, this one, PMGI, again, a polydimethyl glutamate. When we use the base developer, we need 50 microcoulomb per square centimeter. So when we use solvent developer, we need 1000 microcoulomb per square centimeter. So now let's look at the contrast. So obviously, normally we want high contrast. So when we have high contrast, it gives you steeper side walls. You can see steep side wall and sloped. This one not steep. This is low contrast. Low contrast give you sloped side wall. This is high contrast give you steeper side wall. A greater process latitude. That means you can exposure. If you exposure those higher or lower, you get similar result. A better resolution, higher aspect ratio structure, and less sensitive to the proximity effect and higher density pattern. You can achieve high density pattern. We have high contrast. High contrast normally give you a high resolution. So the low contrast resist is only good for the grid scale lithography. So we will see grid scale lithography later on. So normally, obviously, so what do we want? So we want both high sensitivity and high contrast. But unfortunately, as you see from this curve, there is no resist that has both high sensitivity and high contrast. So this curve is compiled by Dr. Alcola from the Argonne National Lab. So those are the popular resists. So here we will talk about HHQ, PMA, and then ZEP 520. So other people, they also use those resists. But those are chemically amplified resists. So here is the dose. So higher the dose, lower the sensitivity. This one is the minimum feature size that can be attained. So obviously, the smaller feature size, the higher the resolution. So as you can see here, when you need higher resolution, you go to higher doses. That is what I said here. So when you want high resolution, you lose the. When you want high resolution, you have low sensitivity. So now let's look at several popular resist materials. The first one is obviously we should look at the PMA. So this is the chemical structure of the PMA. It is the polymethyl meth acrylate. This one was discovered in 1968. And even today, for the beginners, people still use PMA as the resist. So why people use this one? Because it is very cheap. It costs no money. You can buy the 500 kilogram. You buy 500 kilogram, maybe $100. And this one it can last forever. You just buy the powder, you dissolve in the solvent, then it will be good to use. So very cheap and lasts forever and easy handling, and it's very easy to get very high resolution and contrast. So even the beginners, they can get good results with using the PMA resist. So typically, people prefer to use the higher molecular weight, but actually this is not so critical. Even though low molecular weight, like 15 kilogram per mole, is also good. But don't use below 10 kilogram per mole. If it is below 10 kilogram per mole, then this will be the property will be not good, because this is the threshold development by the developer. As long as it is well above 10 kilogram per mole, it should be good. But normally it's dissolved in the chlorobenzene. So when I was a PhD student, we use chlorobenzene a lot. But nowadays I see nobody uses chlorobenzene because people use any salt. So any salt is less toxic than chlorobenzene. This is the chemical structure of any salt, OCH3. So we use this solvent for the development of for the solvent to dissolve the PMA for the spin coating. So the developer mixture can be adjusted to have the different contrast and sensitivity. So we will see this later on. Next slide. So the problem for the critical PMA is that it has low sensitivity. They need a longer exposure time, a poor dry etch resistance. That means it is not a very good etching mask. If you want to etch silicon using the PMA as the etching mask, this will not last very long. So below are the typical doses. For example, so normally we use 30 keV. The 30 keV for the area dose is 250 microcoulomb per square centimeter. So line dose 1.3 nanocoulomb per centimeter. Dot dose is 1.5 femtocoulomb. So this one is for the developer MLBK and IPA 1, 2, 3 diluted. So we will see the developer on next slide. So what is the definition of area dose? So when we talk about area dose, that means you have a big area. For example, you expose the area like 100 micrometer. So that's a big area. So how big area is big? So this depends on the range of the backscattering, so the range of the proximity effect. So as long as the size, as long as the pattern size is bigger than the range of the proximity effect, then we consider this one as the area exposure. So for the line dose, for example, this is 1.3 nanocoulomb per centimeter. So we can try to convert this line dose to area dose and see what happens. So line dose, so normally we have this 1.3 nanocoulomb per centimeter, you get a line. But this line, the line width is not zero. So the width is about 20 nanometer. So you do one single line exposure, you end up with about 20 nanometer line width. From this one, we can calculate the area dose, because the area dose is given by the 1.3 nanocoulomb divided by the area of this line. So the area of this line is 20 nanometer times 20 nanometer. So here we assume like 1 centimeter. So 1 centimeter long line, so we have 1 centimeter. So you can control this. You can convert the nanocoulomb to a microcoulomb. You convert this nanometer to centimeter. In the end, you get a number of 650 microcoulomb per centimeter square. You get 650 microcoulomb per centimeter square. So you compare this number to this number. So normally we said the area dose should be 250 microcoulomb per centimeter square. But here, when we export an isolated line, we get 650 microcoulomb per centimeter square. So then the question is, so how come this number is so much bigger than this number? Yeah. So this is because of the proximity effect. So we export a large area like this. We export this large area. For example, if we take a line inside. You take a line inside. So for this line, you have exposure not only from the direct exposure, but also all the patterns nearby. So when you expose all the nearby patterns, they all contribute to the exposure of this line because of the proximity effect. So as a result, this one you need a lower dose. But when you expose one isolated line, no pattern nearby, then you need a higher dose because you have no contribution of the proximity effect exposure. So this is a very important concept, and I hope you can understand this very well. So this is the developer of the MIBK. So normally people use this is the developer for the PMA. So normally people use MIBK as the developer. So this is the methyl isobutyl ketone. So this one can be diluted by the isopropanol IPA. So when you have 1 to 3 diluted, so this is 3 IPA, 1 MIBK, you get low sensitivity, high resolution. When you get low dilution, you get high sensitivity and high resolution. And then when you get pure MIBK, you get very high sensitivity, then you have got low resolution. So as you can see here again, so higher sensitivity always comes with the lower contrast. So in the end, depending on what you want, whether you want high resolution or you want short exposure time, you can determine what solvent you want. And normally when people in the research, people want very high resolution, then they just use this 1:3 ratio for the development. So another choice is the cellulose and the methanol. So I have tried this one, but nowadays nobody uses this one. The third one is the MEK, methyl ethyl ketone and ethanol. This one also works well. The last one is IPA and water. Isopropanol and water at the 7:3 dilution ratio. This is a co-solvent system. That means IPA will not dissolve exposed PMA. Water will also not dissolve the exposed PMA. But when you put them together, the PMA gets dissolved. The exposed PMA gets dissolved when you put them together. This one people use much popular. This one people use it sometimes. So the advantage for this one is that this is a weak solvent. So it will not swell the PMA. So this one will swell. So this one, the MLPK will swell the PMA a little bit. We use water and IPA, there will be no swelling. But there may be some residue layer left behind if we use this developer because it is too weak. So we know that the main problem for the PMA is the low sensitivity and the poor action resistance. So to solve this problem, in the 1990s, a Japanese company, Zion, they developed a resist they called ZEP520. The main component is this copolymer. So this is the component of this ZEP520. But this resist, they have higher sensitivity than PMA and also higher action resistance. So why this one is more resistant to action than this one? So why this one, PMA chemical structure, this one is low resistant to action. So because this is a linear polymer. But for this one, we got this phenyl group. So we know that this benzene ring is very chemically stable. So this one is hard to add. That's why it is more resistant to action because of this phenyl group. But this one is very expensive. It costs a few $1,000s. So as we said, for the case of PMA, it costs maybe $10. You buy the powder, you mix in the solvent, it costs $10. But for this one, it costs $4,000. But the good thing is that recently, because this one was developed in the 1990s, so that the patent got expired. So when the patent got expired, so there are a few other companies that have the ZP replacement. So the cost will be much lower. So one of the companies it is called All Resist. This is a German company, but they sell the resist. They don't call it ZP520. They call it another name, but the property is really similar and the composition is also similar. So the developer for the ZP is normally people use amyl acetate. You can also use xylene developer. For the solvent, again, people use anisole, the same as the PMA. This one, as I said, it is not toxic. The next example of the resist is HHQ. HHQ, this is the hydrogen sulfate quioxin. You can see this one is very different from polymer. So first, it is inorganic material. So the structure you see silicon, oxygen, silicon, oxygen, silicon. It is pretty much similar to SiO2. So the chemical structure is similar to SiO2, but it is like a box. This is what you can see is like a box structure. So when you do the EV exposure, this box will get collapsed. When this one gets collapsed, the box gets collapsed, it becomes a silicon dioxide. So the developer people normally use as a base developer like a sodium hydroxide, or you can use another base that is the TMAH. So TMAH is also the developer for the photoresist. Why we use TMAH rather than sodium hydroxide? Because this one has no metal. This is the tetramethyl ammonium hydroxide. So tetramethyl ammonium hydroxide. It is similar to this one. So the structure is similar to NH4OH, but the difference, so this one, the hydrogen here, is all replaced by the methyl group. But this is a good developer for the HHQ. So the advantage for this resist, because it becomes a silicon dioxide after the exposure, it has a very strong adhesion and also it is action resistance. So we have very thin film. If the film is less than 25 nanometer thickness, we have very thin film. So this resist gives actually the record resolution for the EV lithography. It gives you 9 nanometer pitch. So 9 nanometer period, 9 nanometer pitch line array. This is the record resolution for the electron beam lithography. This is attained using this HHQ resist. We have the very thin layer, and this oxide is much more stable than PMA, than the polymer. We have very narrow lines. That's why it gives you the record 9 nanometer pitch resolution. But this is why you need a higher exposure dose. It is even less sensitive than PMA. So the last one is the SU8. So we have talked about SU8 when we talk about the LIGA process. X-ray lithography. So when we talk about X-ray lithography, we said this people can use SU8 to have very high aspect ratio structures. This is called UV LIGA lithography. So this one is also resist for the electron beam lithography. We know that it is chemically amplified resist. So chemically amplified resist, that means we need baking the resist on the hot plate after the exposure to induce the chemical reaction. So as a result, it is very, very sensitive. So the sensitivity is 100 times that equal to PMA. For the PMA, we need 250 microcoulomb per square centimeter. For the SU8, we just need 3 or 4 microcoulomb per centimeter square. But as we know, we have very high sensitivity, you get low contrast. This is also the case for the SU8. The contrast is only 0.9. For the case of PMA, the contrast is about 5 to 10. So when you have a low contrast, you cannot have very dense patterns. But for the sparse patterns, for example, for the sparse patterns, you still get high resolution. You get 24 nanometer for the sparse patterns. But here the pitch is, 300 nanometer. It's very, very sparse. We have this pattern, you get trouble. So because of the very high sensitivity, you get the noise. You see the line is rough. This we have seen the term called line edge roughness, LER, line edge roughness. When we do the EUV lithography, we got this line edge roughness, and also you have the residue. You can see the bottom one; they are not smooth. But this is because it is so sensitive. Any random things will show up. It's too sensitive. But this one will be good for the low resolution because we have low contrast. It's good for low resolution, large area because it is very sensitive. We can expose large area without too long exposure time. So for the research, we often do the lift-off process. For the lift-off process, ideally we want this kind of undercut. We want undercut profile, so something like this. So you have the resist, you coat the metal, you get a good, easy lift off. On the other hand, if the resist profile is something like this, right. So if the resist is something like this, then it will be not good. You can imagine when you coat the metal will be coated here and coated here and coated here. But there will also be metal on the side. There will also be the metal on the side wall. You can see the metal on the side wall will connect the metal on the top and also metal on the bottom. Then even though you dissolve this resist, the metal on the top is hard to get off. But we have the undercut, we have the opposite, then you get easy lift off. But to do the e-beam lithography with lift off, so normally one popular method people do is they use they call it a double layer. For example, you have the top layer as the resist, you have the bottom polymer layer. You do the development, then you dissolve the bottom layer by a solvent or liquid, you get this undercut profile. So one popular material for this undercut, this layer is called LOR. It's called lift-off resist. Lift-off resist. It's also based on the PMDI. So this LOR is based on the PMDI. Polydimethyl glutamate. This is LOR. Another pair of the resist that you can also choose is the PMA and the ZAP. The PMA and ZAP. The ZAP is this one. You can put this one at the bottom layer. So because the ZEP, this one is more sensitive. So we do the exposure of the holes. Exposure of the hole. The top hole may be this big. The bottom hole will be bigger. So this will get this undercut profile. But this hole is bigger than the top one because ZEP you need less dose. It's more sensitive than PMA. So now let's look at a grid scale lithography. So the idea is similar to the grid scale lithography for the optical lithography. So you vary the dose to have different pattern depths. For example, you have higher dose here, lower dose here. After development, development, you get something like this. You can also do the pattern transfer into the silicon to make some structure like this. This one we call it a fractional zone plate. So the idea is similar to the zone plate we learned for the X-ray lithography, but the difference is that for the zone plate for the X-ray lithography, so we block half of the light. For this case, the light is transparent everywhere. The light is transparent everywhere. You may wonder how come silicon is transparent. This one, the wavelength is 1.55 micrometer. This is the infrared light. So silicon is transparent to the infrared light. So now I will show you how this fractional zone plate, how this fractional zone lens is designed. Yeah. So this is how the zone lens is designed. So normally we know the lens is something like this. So the lens is something like this. So then what we do? We cut away this those shaded region. Then we cut this away. Then we bring this part downward. So we bring this part downward. We bring all them down. How much we need to cut? So we need to cut such that the optical path along this is the integer number of the wavelength. For example, this one may be 10 lambda. This one may be this is 10 lambda. This is 11 lambda. So this is 10 lambda. Then you have this another one, 9 lambda. We'll remove the integer number of the wavelength, the n lambda. Then the light focusing will be the same. Because anyway, the light, when it goes through the n lambda, the phase will be the same. So this is the idea. This is the idea of this fractional zone lens. So for the grid scale lithography, so what resist we want to use? So the ideal resist should have very low contrast. So you can imagine if the resist had a contrast curve like this. If the resist has a contrast curve like this, that will be good. Because when you change the dose, you can change the pattern height linearly. Or maybe this is the case for the positive resist. Everything negative resist, something like this. This is also good. So you change the dose, you change the height linearly. But this is a very low contrast resist. So we have very high contrast. For the PMA, we have very high contrast. If we have sharp slope, then this will not be very good. Because if you change the dose, a little bit, you change the pattern height a lot. Then it will be difficult to control the pattern height. So this is why not good. So this is the PS resist. So this is why you can see this is the contrast curve. The contrast here is only 0.8. This is pretty low. This is good. You can vary the dose. You can vary the dose to have different height easily. So now let's look at anti-charging technique. So we know that. So normally when we do the e-beam lithography, we work on the silicon. So we have the resist like a PMA. We have the silicon. The silicon is semi-conducting, but actually the conductivity is good enough. But even though the resist is polymer, is insulating, this is not a problem because most electrons, they just penetrate through the resist, go to the silicon, then the charge will be dissipated. This is not a good problem. But if you want to do the lithography on top of the glass, then the charge will be trapped. Then you got the trouble. You can see here, when you do the exposure, there will be lots of negative charge. But when the future electron come in, they will be repulsed by the Coulomb force. Then this way, the placement of the beam will be wrong. Then you get the pattern will be distorted. So we have the same problem when we do the SEM imaging. So one obvious way to solve this problem is to coat some metal layer. So we coat some metal layer on the top. You get the pattern. You can dissipate the charge. Usually we can coat aluminum, titanium, chrome, or gold. But actually we want a lighter metal. Because the lighter metal, the scattering will be less. If we have a gold is very high atomic number. Then if we have gold here on top of the PMA, when the electron come here, it will be scattered too much. Then the pattern, then the pattern design will not be very good. But usually we want light metal. For the casing of aluminum or titanium, they can be removed by very diluted hydrofluoric acid, like 1 to 100 diluted. This very weak acid, very diluted weak acid, will not attack the resist. So here you see the result. This one, when you coat the metal, you have no charging. When you no metal coating, the pattern gets distorted. In the recent years, people also try with the polymer coating. So they use semiconducting polymer. For example, this one, P dot PSS. The name is complicated. But this one, P dot PSS, this is a conducting polymer, and it is soluble in water. So what you do, you have the resist, you coat this polymer on top of the resist, then you do the exposure. So afterwards, you can use water. You use water to remove this conducting polymer again. Then you do the development. This way, you do not need high vacuum metal deposition by evaporation or by sputtering. But the problem, so those polymers, they are not cheap. You buy a small bottle, it costs maybe $1,000 or $2,000. As a result, the people still use, they use the metal coating very often. This is the first method. We use metal coating to get rid of the charging effect. The next method is called the variable pressure. The variable pressure lithography. The idea is similar to the variable pressure SEM. So what do we do? So normally we know when we do the imaging, we need high vacuum. But in this case, we have some gas molecules like water, nitrogen, argon, or helium in the chamber. For example, we have the water molecules. We have water in the chamber. So here is the wafer. So when the electron come in, it will hit this water molecule, and it will be ionized to have some positive charge. Then this positive charge will migrate to the surface. You have the positive charge migrate to the surface, and below you have this negative charge. This negative charge is come from this electron beam. Then those positive charge will cancel out, will balance those negative charge. In the end, you don't have the charging effect. Here is the example for this variable pressure electron beam lithography. This is the nuance. This is the Northwestern University Atomic and Nanoscale Characterization Experimental Center. This is the this work is from the Northwestern University in US. So this one is the high vacuum. You can see the pattern, they are not well placed. It got shifted. This is 0.4 torr water vapor. This is 1 torr water vapor. We have higher pressure. The charge is better balanced. You see the pattern. They are well placed. So now I want to ask you, so how come the letter E got displaced, but the letter N is good? It's very precisely placed. So that's because the letter N was written as the first. The letter E is written as the last. So when you write the letter E, there are already lots of charge accumulated on the substrate. So that's why it gets more displaced. Yeah, this is the second method to reduce the charging effect. So the third method is called a critical energy electron beam lithography. What is the critical energy? So we know that when we have electron come in, some electron will come out. But this electron can be secondary electron. It can also be backscatter electron. So you can imagine when the electron is very high energy, it goes very, very deep. It goes very deep, not much electron come out. This is the total yield. The total yield of the electron coming out. We have very high energy, they go very deep, not much interaction, so not much electron come out. So you can see the number it drop. Higher beam energy, the smaller the yield of this electron. When the energy is really low, like a DC is just come in, get dissipated. It's also not enough to kick it out, so you get also low. So overall, you get this kind of curve, and this is 1. So the number 1 means you have 1 electron come in, 1 electron come out. This way, there will be no charging. There are 2 energies for this sigma equals to 1, E1 and the E2 value. But this number here is too slow. It's too low. It's not useful. So this one can be the range for the electron beam lithography. For example, so when we have 65 nanometer PMA on the glass, then this one is 1.3 kilo electron volt. This one we can do when we do the electron beam lithography at the 1.3 kilo electron volt, then there will be no charging effect, because as I said, so one electron come in, one electron come out. So in the end, there's no charging effect. So now the question is, how to determine it is 1.3 kilo electron volt? This is determined by using this method to find how to find this E2 value. So what do you do? First, you use the high magnification. So in this case, it's 500 times magnification. So to scan this area, inside, to scan this area. Then you zoom out to use 200 magnification to have this bigger area. You can see this one this is dark, this is no contrast, this is bright. So when it's dark, this is the 0.5 kilo electron volt. It corresponds to, for example, this spot here. So the sigma is higher than 1. So that means you have 1 electron come out, you have maybe 1.5 electron, 1 electron come in, you have 1.5 electron come out. This way, this area will be positively charged. You have more electron come out than electron come in. It is positively charged. So this positive charge will pull this one back. Because of the attractive force, you pull it back. That's why you get smaller signal from the center part. It appears dark. We have 2 kilo electron volts. It comes to here. So the substrate will be a negatively charged. So this negative charge will help this electron come out. So this one will help electrons to come out. So you have higher signal, brighter, higher signal in the middle part. We have 1.3 kilo electron volts. You can see the center part and the offset part, they have the same contrast. Same brightness. This way we can figure out that the energy for the E2 is roughly 1.3 kilo electron volt. So the next topic is the electron projection lithography and multi-beam lithography. As we know, in the 1980s, electron beam lithography can have very high resolution. In the 1980s and in the 1990s, people believe that one day electron beam lithography will replace the optical lithography for the IC manufacturing. But the problem for the electron beam lithography is that it is very slow. If we use single beam, it is very slow. It's only good for the research, not good for the production. So how to do the production using electron beam lithography? There are 3 ways to do this. So the first one, we use the broad beam. So this is like an optical lithography. It's similar to the optical lithography. So we use broad beam. So electron beam has very short wave loss compared to the light. So we can have very high resolution, much higher resolution than optical lithography. This is called the scalpel. So we'll see the scalpel later on. Second way is we start from a broad beam, then we divide into many small beams. The third way is we use many small beams. When we have many small beam exposure at the same time, then the throughput will be higher. So now let's look at the third one first. We have array of the many electron lines. So you can see here, this is it's called the field emitter array. You have very sharp tip. You apply the voltage, so the electron will come out. So we have many such kind of beams. You get very high throughput. But the problem is that you cannot have any lenses. It's very hard to control. As a result, this one is far away from the mass production tool. Just for some research group to this, but it is not very useful. Not useful for the production. The second one is this one, broad beam. So this is like a photolithography. For this one and for this one, we generate the pattern by the exposure using the electron beam. For this one, we copy the pattern from the mask. This is like a photolithography. We have broad beam. We duplicate the pattern from the mask onto the substrate. For the mask, because electron can penetrate very deep, electron can penetrate, for example, 10 micrometer. So electron can penetrate into the silicon by 10 micrometer, but you cannot make it's very difficult to block the electron beam. When you make this height 10 micrometer, then you lose the resolution. As a result, we do not block the electron beam from the mask. Instead, we just scatter. It's called a scattering mask. It is not an opaque mask. It is a scattering mask. So when the electron hits the metal part, it got scattered. Then we have the lens. You can see. Then we have the small aperture here. So only very little electron can come in. Then this will not be exposed. When the electron comes to the membrane part, it's not scattered. Then most of the electron come in. This part is got exposed. So this way you can do the lithography. You copy the pattern of the mask onto the wafer, similar to the optical lithography. But the problem for this one is similar to the acrylic lithography. This one is the fragile in membrane. This is the very thin silicon nitride membrane mask. We have membrane mask, it will break very easily. It's not stable. That's why in the end, this does not work. But this work was done in around year 2000. Around year 2000, it mainly done by the people from Bell Lab. Done by the people from the Bell Lab. So we know that the Bell Lab is really, a very famous age discovered transistor in the 1940s. But nowadays, nobody knows the Bell Lab because Bell Lab got bankrupted about 15 years ago when there is the telecom bubble. The third one is this one. So we start from a broad beam, we divide into many small beams. This is the case. One of the examples is by this mapper. So mapper is a company. So mapper is a company. From the Delft. Delft University from the Netherlands. Delft University from Netherlands. This company was established in about 2000. Here is the idea. First, you have the electron source. You have the very broad beam. Then you have this aperture array to divide into many small beams. Each of the beam will be controlled by this light. So this one is called a phototransistor. So this one, the light. You use the light to turn on or turn off the beam. Use the light to turn on or turn off the beam. This is the beam blanker. Then you do the parallel exposure. This one was considered by the scientist called Berlin. So here is the CTO of the TSMC, Taiwan Semiconductor Manufacturing Corporation. So we know that about 10 years ago, EUV lithography at that time, so EUV lithography had no hope, very low EUV power. So at that time, the mapper was considered that will replace the optical lithography. But today we know that the EUV lithography absolutely win out. The mapper will not be used for the mass production of the IC chips because EUV lithography is doing the work really well. So there's no place for the mapper. But nevertheless, because when you do the mapper, you do not need a mask. When you do the EUV, you need a mask. So the EUV mask, a setting of the EUV mask will cost several $million. But when you do the mapper process, you do not need any mask. You just do the exposure. You do the pattern design, you do the exposure. So as a result, this company, even though they are not so successful to replace the EUV, still they survived. They provide the prototyping service. If you want to make small quantity prototype, then this will be very good because you don't need to make any photo mask. So now I will show you a video for the mapper. I will show you a video for the mapper process. The beam blanker. a photo transistor to control the beam on or beam off. But this is raster scan, not vector scan. Okay, thank you.